If quantum computing gives us no advantage this decade, and it doesn't, then why does Kronos map out exactly where it would help fusion? Because the applications are real even when the hardware isn't. Knowing precisely which problems are quantum-shaped is how you stay ready without fooling yourself. The most natural fit is quantum chemistry. The hardest materials questions in a fusion reactor are quantum mechanical at their core. How electrons arrange themselves in a Rebco superconductor, or how the first wall holds up under relentless neutron bombardment. These are the properties that classical methods approximate, and that a quantum computer, in principle, could compute directly. That is because a quantum computer speaks the native language of molecules and lattices. Simulating how atoms bond and how electrons correlate is exponentially hard for classical machines as the system grows. A quantum computer represents that same quantum state naturally without the exponential blowup. This is the one domain where the theoretical case is strongest and least speculative. Push further, and you reach the many-body problem. Many particles all interacting at once, the knot at the heart of both material science and plasma physics. Classical computing bends under it. It is a natural long-term target for quantum methods, though for the plasma itself, the target sits well beyond today's reach. Beyond chemistry, there are two more speculative angles we track. Quantum optimization, algorithms like QAOA, could one day search enormous design spaces, hunting for the best magnet geometry or operating point. And quantum machine learning proposes running the learning itself on quantum hardware. Both are genuinely interesting. Both are honestly the far edge of the map. So we hold a roadmap, not a fantasy. High-performance classical computing does the real work today and for the foreseeable future. Quantum enters as a hybrid partner, first on small, well-chosen chemistry problems, later on larger ones as the hardware matures. It is a pipeline over time, with classical carrying the load and quantum proving itself on narrow, verifiable tasks. There is also a deeper physical thread that ties quantum straight back to our machine, and it runs through helium-3. The most sensitive quantum hardware has to be cooled to a whisper above absolute zero. Dilution refrigerators reach below 300 millikelvin, and the only working substance that gets you there is helium-3. Below that temperature, there is no substitute, and helium-3 has been rationed since 2009. That is not a coincidence Kronos treats lightly. Our breeder, Hyperion, produces helium-3 as a bred output, roughly 9/10 the mass of its tritium. The same isotope that a quantum computer needs to reach its coldest states is one of the materials our foundry is designed to make. The quantum industry and the fusion foundry meet at the cold edge of physics. But let me be exact about that link, because it is easy to overstate. Helium-3 supply and quantum computation are connected through the refrigerator, not through the algorithm. Making the isotope more available helps the whole low-temperature ecosystem. It does not, by itself, deliver a computational speed-up. Two real things, honestly joined, not one miracle. So the verdict for applications is the same one we give for the hardware. No quantum advantage this decade. The chemistry case is the strongest and worth preparing for. The optimization and machine learning cases are further out, and the honest connection to our own machine is a supply of helium-3, not a shortcut through computation. We publish all of it: the roadmap, the resource estimates, the caveats, with a permanent public record anyone can audit. Because the value here is not a bold promise. It is a precise map of where a powerful, unfinished technology will and will not help, so that on the day the crossover arrives, Kronos is already standing at the right door.